Hello and welcome back. Integration revision for year 13, questions 128 to 138. And you can see from my dress today, we must be approaching Christmas. I'm recording actually well ahead of Christmas, so I hope I remember to put the video out, upload the video at the right time. So Merry Christmas and a Happy New Year to our users, or to the users of our site, and to the subscribers of our channel, and anybody else who likes us and supports us. Okay, and a very special Merry Christmas message for a special teacher that a couple of your students, Mrs. Bradley Brophy, got in touch with me. I hope I'm pronouncing your name correctly, from Northampton School for Boys, and I don't know if I should actually mention their names. Well, I'll mention the first names. Will and India got in touch with me and said to wish you a Merry Christmas, because you are their favorite teacher and they love you very much, and they know you've been working very hard in the school all this time. Okay, so Merry Christmas and a Happy New Year to you especially. Okay, let's return now to our integration. This is now the questions 128 to 138 to go through. I think I'm gonna probably end up with one more lecture, finish it off to 150, to a nice round number. I think it's more than enough integration for revision. And for today, I think this is quite a tough session. So let's write the first integral. This is the integral of 3x minus 1 over 2x plus 3 dx. Okay, how do we do this particular integral? We have a choice of methods. The teacher's favorite for this one is, of course, a little long division for this particular one. The second choice is a substitution. U is equal to your denominator. And mine, I'm going to actually do it slightly differently. It's actually a division without really dividing as such. Just to give you a little bit of practice with how I manipulate things. It's very difficult to actually put notes for that. You need to see it live. I'm going to write a 2x plus 3 here, and I'm going to put in a bracket, not that it needs it, but just to actually see what I'm going to do. And I'm going to write again 2x plus 3 on the top, and now I need to balance it and create first of all a 3x. Very easy to create the 3x by putting 3 over 2 in front of this bracket. There's my 3x now. But now I created a 9 over 2 positive. I need a minus 1. You can use your calculator, or you can do it in your head if you're good. Minus 11 over 2. That's still exactly the same now. So I just rewrote my numerator from 3x minus 1 to this particular form. That divided by that minus 11 over 2 divided by this denominator. Split your fraction. 3 over 2 minus, I'm going to write 11 over 2 on the top, like this. 2x plus 3 dx, and that is, of course, done. 3 over 2x, and that's the log of mod 2x plus 3. And this creates, of course, a little chain from the 2x divided by 2. So the 11 over 2 will become 11 quarters plus c. Okay, number 129 next. So 129, looking at it, is of the same theme, only a little bit harder. I grouped those two together in my book purely to give you a little bit of practice. So the way this is done is exactly the same as 128. Same choices. Either a long division, probably safe to do that. Either a substitution. Better choice for this one actually to go for substitution on this one. Substitution, use your denominator, of course, and it can be manipulated like this, which I'm going to show you. So how will I manipulate that? Well, it can be done as it is, but probably it's a better idea to swap this into a 2x minus 1, and I've done that by putting a minus outside the integral. So the minus that I pulled outside minus on the denominator. So that's exactly the same. dx. And now comes the splitting. Big fraction line, 2x minus 1. Everything must have this quantity in order to split. Let's start with the 2x minus 1 on the top, and let's create the 8x squared. How will I create an 8x squared? Very easily. There's my 4x in front of this bracket. There's my 8x squared. Okay, I created now a minus 4x, which I need to get rid of. Let's put the bracket again here, 2x minus 1. And I need a plus 4x. So plus 2 there. There's your 4x gone. But I've now created the minus 2. Let's put the plus 2 there to balance it. And now that, it's exactly 8x squared, but I can split it 3 ways. And the split, of course, is going to be, I forgot the minus there, I'm the king of mistakes, minus 4x, that divided by that, plus a 2, that 2 there, and then of course that 2 still to be divided by 2x minus 1 dx. And all I'm going to do is my final line, the final integration. I'm going to integrate and do this minus at the same time. So I got 2x squared with a minus from the front, a 2x from this with a minus, and this is a simple log mod 2x minus 1. And of course, the chain will get rid of this 2. That's meant to be a 2, it's very badly written. 2 divided by 2 is 1, but of course from the minus at the front we got that plus c. So that is 129 done. 130 comes next. 130 is actually very easy. And I think just looking at the page, this is quite a demanding set, the 128 to 138. So it's nice to have something a little bit on the easier side to give ourselves a little break and a little breather. I'm gonna get out of the way. Sorry, I can barely read this, and I'm in front, but I will move. This is the integral in question. Very easy. Does not require anything really. It's linear of the form ax plus b. No x's on the top or anything funny. So this can be done by writing it as 10 bracket 3x plus 1 to the power of minus 3 over 2 dx. So this is what I normally call linear adjustments. So it starts from differentiating a higher bracket, by increasing the power by 1. So it's going to be to the minus a half. And we adjust the constant at the front. 3 minus a half times 3 is minus 3 over 2. And 10 divided by minus 3 over 2, I'll make it 20 over 3 negative. I hope the minus shows on the video. Minus plus c. Of course, you are allowed to use your calculator, and therefore you don't have to do it in your head or anything like that. Okay, what comes next now? What comes next is actually a very quick integral. That's number 131. But we might need to discuss this a little bit. It doesn't come up that often. I don't know about other boards. I haven't kept in touch with some of the boards in recent years, and I mainly follow the Pearson Edexcel, but I know this particular integral has come up, I think 2015 or 2016, and before that, I think 2012 or 2013 on the C4, of course, in the older spec. So this is the integral of 5 to the x dx. Interesting, because of course we used to integrate exponentials, the exponential function, but not ordinary exponentials such as 5 to the x. Okay, this is actually very easy to integrate. I'm going to show you 2 ways. First of all, let's do a little bit of differentiation on the side here. The differential of a to the power of x is in fact where a is a positive number, can be negative. It really shouldn't really be equal to 1 either. It's a trivial case. So if it's it can still be 1, but it's a bit stupid if we leave 1 there. So this is non-negative. Is actually equal to a to the x log of a. There's a couple of ways to prove this, and it's part of obviously the course. So if we differentiate, just look at a few examples. D by dx of 2 to the x is of course 2 to the x log 2. D by dx of 3 to the x is going to be 3 to the x log 3. And of course, it works with the exponential function, function. If you think about it, this one, of course, we know what that is equal to, but it does follow the rule. It's of course e to the x log of e. But this is very special. The log of v, of course, is 1. So if we look at our own, d by dx of 5 to the x should be, of course, 5 to the x log 5. So all exponentials come from differentiating exactly the same exponential. So it's not a bad guess to say, okay, I need to differentiate a 5 to the x to get something like this. Okay, but this produces extra bits. If you look at the 5 to the x, when I differentiate it, it will produce this log 5. And therefore, I need to get rid of this log 5 that will be created from the differentiation. So the way I will deal with it is to divide by the log of 5 plus c. So this will differentiate. If we look at this differentiation very, very quickly, d by dx, 1 over log 5, 5 to the x. The 1 over log 5 is just a number, it's just a constant. Now 5 to the x will differentiate to 5 to the x times the log of 5, and of course the log of 5 will cancel to give me the required answer. It can also be done, I don't know if I want to show it here. I did say I'll show you another way of doing this, but I don't know if that's going to be a bit confusing. We can write the 5 to the x as e to the log of 5 to the x, because of course e and log are inverse functions, and therefore they will cancel each other. So why do I want to do that? Well, quite clearly I want to use the rules of logs on the exponent. So I can write this as e to the x log 5. So that's just a number. It's like when you're writing e to the 5x, you got a constant, that's your constant here, times x. And of course, if you had to integrate that, you know how to integrate that, is of course e to the 5x with a 1/5 at the front, because that's your constant. So it's exactly the same thing here, that's just a constant. So that comes from, or rather integrates to, x log 5, and you're going to put 1 over the constant, log 5 plus c. But if you look carefully at what is that, well, you can put that x back up here, and of course all of this is your your 5 to the x, which we constructed there. So that's another way of doing the same integral. Most of the time, I think when I was a student myself and I came across it, it's not too difficult to kind of like almost memorize it and just say, okay, if I get something like that, I just need to treat it as a special case, and that's how it's done. Okay, so I didn't write a number, that was number 131, which I'm going to rub off in a minute, and I'm going to go to number 132 next, which is not a pleasant looking integral. Okay, let's have a look what it has. Integral, we have a square root sine x cos squared x, all inside a square root. Not very nice. What I'm going to do, first of all, with this square root, how that fits. A few things could go through our heads when we first look at this. We can think perhaps switching that to 1 minus sine squared, multiply it out. Still the square root is there and very painful. What else can we do? We can write this this radical as a sine x, and then we can borrow one of the causes perhaps. So that's your cos squared. Put a 2 at the front and then a half. Write as a half sine 2x cos x. But the real problem is still in there. We can use a substitution, because when we have something which we don't like, we normally say, okay, let's get rid of it. And we can't just throw it away, of course. Let's call u is equal to perhaps that, and this will not work very nice either. It's no problem trying things. Substitutions, of course, is the favorite thing to do. If you can't see what to do, try a few substitutions. So if we now stuck with, we tried the 2 or 3 things, probably we'll think about perhaps taking the square root of this. And I'm going to write this as the square root of sine x times the square root of cos squared x dx. And so I don't complicate things. I think most of us at straight maths will not really be bothered with that, and you'll be happy if I write that this, of course, is the same as the cos of x. There's a few people that might take offense to that and might take exception to that. Let's assume, let's not worry too much about it. Let's imagine that the cos of x is an acute, so not the cos of x, the x is an acute angle, or x, perhaps if not an angle really here, is some number between 0 and pi over 2 inclusive. Okay, it can't be for minus pi over 2 because we're going to have a problem, of course, with the sine trying to take a square root. Okay, so at the moment, if you cannot see any problem with that, please forget what I just said, by the way. Just ignore it. The square root of something squared is, of course, just the cos of x, and we're happy with that. So I'm going to write this to the power of a half. It's the same thing. And then re-examine this integrand and let's say, okay, what can I do in there? Maybe I can try substitutions again. What substitution? We got really two realistic choices. Either u is cos x or u is equal to sine x, really could be possibles. And you'll find if you use a substitution, u is equal to the sine of x, this actually will clear. So it's actually, assuming we thought of that, and we got this stage and we try the substitution, this should work fairly straightforward. I'm not going to show this method, so I'm going to actually show how to do this now without a substitution, because of course this is recognizable. We can write an answer straight away for that if we are very good at all of this. The sine at the power, some power with the cos next to it, is very special. It's because sine differentiates to cos, and therefore what I'm looking there is a differentiation. I need to recognize the chain rule. So the sine of x starts from a higher power, one higher, 3 over 2. Let's see what happens if I differentiate that. A 3 over 2 will come to the front. The sine of x will go, of course, to the power of a half, and of course times the differential of that, which is a cos of x. Let's examine what we got in the integrand. We got everything except this 3 over 2. We just need to get rid of it, and therefore 1 divided by 3 over 2 is 2/3 plus c. If you do the substitution, u is equal to sine x, which I'm not showing here, you will get exactly the same answer. So this is number 132. 133, 134 and 135, I would like to actually write all three on the board at the same time, and there's a reason for it. It's because when I put them there, I'm trying to actually teach a particular skill. The skill is actually exactly the same as that of 132, but is in a different setup. So let's have a look at the three integrals. That's 133. My eyesight is getting really bad. I have to take the piece of paper in front of me, I cannot see. 133, integral of 2x plus 1, the sine of x squared plus x plus 1 dx. Integral 134 is 2x plus 1 multiplying the bracket x squared plus x plus 1 dx. And lastly, integral number 135, almost come to the end, 138 up there, is an x plus 1, and then we got the cos, and the cos is x squared, where are we, x squared plus 2x plus 1 dx. So these are the three integrals, and they all have exactly the same theme, and we got to spot what is going on for this. Okay, this one is quite easy, isn't it? We can actually multiply the brackets out. We'll get a cubic. In fact, when I give this the regular homework for my own students, I think the majority of students actually fail to see how to do 133 and 135, and 134. Practically everybody multiplies the brackets. It's not really that hard. It's going to be a cubic. It just takes a few seconds to multiply the brackets, and they get, of course, the correct answer. But it can be done in a completely different way and much quicker, in fact. So what is there to see? Another thing I want to mention, this bracket here, a lot of people see this bracket as the same as a bracket like that. This is not the case. This is the argument of the sign. That's bit is inside the sign, doesn't multiply, doesn't do anything, doesn't follow the rules, the standard rules of algebra. Same thing with this one. That's the argument of your cos. It's inside the cos. Okay, I'm going to use a different color pen. Let me just borrow the red pen and show you what you need to be looking for all of these three integrals. The differential of x squared plus x plus 1 is 2x plus 1. I'm going to write it on the top up there. And the same thing with this one. Okay, and then look what happens with the rest of the integral. That differentiates to 2x plus 1. And if we look at the differential of this argument, which is the bit that's inside the cos, the differential of that is 2x plus 2, which at first glance is not related to this, but if I factorize the 2 bracket x plus 1, that is there. These are the telltale signs of chain rules. Is differentiations that took place in there that we need to recognize and undo. And for the record, because I'm not going to show substitutions, all three of them can be done by substitutions. The first one can be done by the substitution u is equal to x squared plus x plus 1 in 2 or 3 lines. Same thing with this one. U is equal to x squared plus x plus 1. And here, u is equal to x squared plus 2x plus 1, the argument of the cos. So all of these three integrals can be done with these substitutions, but we're going to try to recognize them and write some answers straight away. There's the answer to the first one. Because the argument of the sign is 2x plus 1 on differentiation, and that is there, that is a differentiation that just took place, and this is the chain. So in order to get something which looks like sine, it must be starting from differentiating the cos of exactly the same argument. So that starts life as a cos of x squared plus x plus 1. What happens when we differentiate that? Well, first of all, the cos will go to a minus sign of this argument. We got the sign, but we don't have the minus, so the minus is not there. But of course, then it will also have times the 2x plus 1, which is there. Therefore, the only bit that is missing is this minus. Minus plus c. That's your answer. That's what you'll get if you do a substitution. We're looking at this particular one as well. Yes, you can multiply it out. Unlikely you get something like that in an exam because, of course, you should really get full marks. You just times the brackets out and just integrate like a year 12. So this is just for understanding basically the method. Since this bracket differentiates to 2x plus 1, the interior of the bracket, this quadratic expression must have started at a higher power. What do we mean by higher power? That's to the 1, so it must have started squared. What happens if I differentiate that? A 2 will come to the front. This bracket, of course, will go to the power of 1. And then, of course, we're going to have next to it the differential of that, which is 2x plus 1. We have everything in there except this 2. We need to hide this 2, half plus c. And this is now done. Lastly, this is like this one, but only a little bit more advanced. Because this differentiates to something which we have there, we're just missing that 2. We suspect perhaps we differentiated the sign of exactly the same argument. Let's see what happens. And often when you do this kind of work, it's good to be putting some jottings on the side. So what happens if I differentiate the sign of x squared plus 2x plus 1? Okay, this will differentiate to. First of all, I'll get the cos positive, so I differentiate to plus. So that is differentiates to that times by the chain rule, the derivative of this quantity, which is of course a 2x plus 2 next to it. If we look now at the integrand, we got this cos, and we don't quite have this quantity. I'm going to rewrite it in fact as 2 bracket x plus 1. We got the x plus 1, we don't have this 2. So how can we get the 2 in there? Well, first of all, I'm going to put the 2 here because I need it, and I'm going to stick a half on the outside. So that's exactly the same. So if I look at this quantity here now, that's the differential, the exact differential of this. So this comes now from differentiating the sine of x squared plus 2x plus 1. I'm going to take this off, plus c. And of course, is there anything else to put in there? Well, the half that I pulled outside the integral. So these are the 3 integrals done. Substitutions, which I put there in green, will work. Do not panic if you don't quite ready to see this kind of things. Please rely heavily on substitutions a lot of the time. Are these 3 integrals hard? Yes, they are. Are they good candidates to come up in an exam in the way I just presented them? Highly unlikely. Why I bother to do that is because it's good training for the mind, for integration in general. Okay, so I think these are valuable to actually see things. You might see something else which is related to what we've just done in there, and you find this useful. Okay, let's go to number 136 now. A demanding integral 1 over 2 plus the square root dx. Okay, how do we do this one? Quite obvious. It's got nothing to do with partial fractions, nothing to do with perhaps trigonometric identities. I don't think it's integration by parts. So that cuts out a few stupid choices. So what does that leave us with? Well, I would imagine a substitution, because of course, if you look at this integrand, it's fairly ugly. This is really very, very painful to look at, the square root of x. We'll try to get rid of it, and therefore the substitution u is equal to the square root of x is a good candidate, and it will work. Okay, so this is probably what most people, myself included, when I was learning, I probably would have done in there. Today I'm going to show a slightly different substitution because it's worth seeing a few variants of that. So you can stick with the substitution u is equal to the square root of x. It will work, but there's a better substitution. And can you guess what I'm going to write in here is the entire denominator. Okay, do I differentiate to get my dx from that? No, for something like that, it's probably better to subtract the 2 to the left, square both sides. Let's write it back to front. Let's waste the line. Makes the video longer as well. Now I'm gonna do not a du by dx, of course. I should have done that up there. I'm gonna do a dx by du because it's easier. After all, I can rearrange and get my dx from that. So dx by du is, of course, 2 bracket u minus 2 to the 1, which is fine. And therefore my dx will be 2 bracket u minus 2 du. And now I can transform my integral nicely. That's all 1 over u. That's what I called my denominator. And my dx is, of course, I should really use a square bracket there, square bracket of 2 u minus 2 du. What can I simplify this to? Probably this 2, I'm gonna put it outside the integral. Let me just write it. It's multiplicative, it has no u dependence, and therefore it can go on the outside. And then the rest will be, of course, u minus 2 over u du, which will split. U divided by u is, of course, a 1 minus 2 over u du. And this is now a very easy integral to do. Let's not forget the 2 at the front. This will integrate to, I'm going to use a square bracket, not to evaluate, just purely to do that multiplication there. U from this one here, because the integration with respect to u, minus 2 log mod of u plus c. And if we times this out, we're going to get, I'm going to do 2 things at once. Let me actually do it on the next line. Multiply the bracket and put my substitution back in. So it's going to be 2u, where u is, of course, 2 plus the square root of x minus 4 log mod 2 plus the square root of x plus c. This will be full marks. I'm just going to do a little bit of a manipulation just to show you a couple of other things. Which there's two things that when I'm looking at this that I will probably, me personally, will be doing purely because I like to look at nice things when it comes to maths. First of all, when I multiply this bracket, I'm going to get the 4 plus 2 times the square root of x minus 4 log. This is the positive square root of x plus 2. This is always positive. I really do not need mods there. You might say it's a bit petty. It's okay. Perhaps it is. I've got an OCD perhaps, and I will. No, I don't like to write that. Secondly, this 4 here. This 4, I'm going to bin it. Okay, I'm going to throw it away. Can I do that? Yes, in integration I can. I'm not throwing it away as such. I'm going to put it inside this constant. If you want, you can relabel it to a d, it's no problem. So my final answer for this will be 2 root x minus 4 times the log of 2 plus the square root of x plus c. This 4 I would have thrown it away. Let me just see what the answer is. Not the answer is, the answer I put down. 136. Yes, I have it in this form. That's not there. That there's no mods. You won't lose marks if you just left it like this, so please do not think I have to do things like that, or if you haven't seen it before, or perhaps you're not likely to do it. Okay, 136, 137 and 138, and we are done. What's now on number, oops, I'm pulling, my mic is pulling because I stepped on it. Hope it's not making any funny noises because this mic is terrible. Okay, 137 and 138. No idea what they are. Hopefully they're not too bad. Let's have a look. 137. They're both challenging, I think. This was quite a challenging set of questions, I did say in the beginning. So let's have a look at the next integral. I cannot see readily how to do it either, although I have a few ideas when I looked at it. So this is the integral of 1 over e to the x plus e to the minus x plus 2 dx. Okay, what's going on with this particular one? Again, what should be going through my head is things that I can just say there's nothing to do with that. Integration by parts, by partial fractions, I don't think so. Trig identities, don't be stupid. Some kind of, when I look at this, is perhaps some kind of manipulation, perhaps tidying up this if I can see anything useful, or some kind of substitution. What substitution will I be using in there? First of all, if I was a student, I'd be starting with very simple substitutions such as u is e to the x. I don't think there's much difference if you try u is equal to e to the minus x. They're symmetrical. Or maybe the whole denominator, and hopefully see where it takes it. There's one more thing that is in there, and people that see a little bit far ahead, can you see a perfect square on this denominator? I don't know if it's relevant to this question, but let me just show you. If you look at this bracket that I'm writing now, this is the denominator, by the way, plus e to the minus half x all squared. Square of that is e to the x. The square of that is e to the minus x. And when you multiply them together, you get a 1 times 2. That is your denominator. Those who are doing further maths and are good with integration, full stop, can actually do that in a completely different way. Because, of course, this quantity, that's your denominator, if written like that, is very, very special. It has a name. This is 2 lots of the cosh. For straight mathematicians, please ignore what I'm writing in here. So people that just happen to be aware of these things here. So that's 2 lots, because normally we'll have halves in there. The cosh of half x. And of course, all of this is squared. And when we unsquare it, we're going to get 1/4. That's 1 over 2 squared in there. And the cosh, I can write it on the top as a sech of half x with a square in there. So I missed the integral signs, integral sign dx, dx, dx. And if you look at this particular quantity, if it was to be integrated, sorry, I'm just a bit sloppy with my notation there. A set comes from differentiating, I think, a tanh of exactly the same argument. So if you differentiate a tanh of half x, you'll get set squared of half x. It also produces a times a half to come to the front, and a quarter divided by half is of course equal to a half. So this could be one of the possible answers. I hope I haven't made any mistakes in there when I've done this particular one. But of course we're in straight maths, and so a lot of people would be say to me, come on man, stop it, this is a stupid what you're writing up there. And perhaps it is. Can it be done in a different way? So what would a straight mathematician be thinking? Of course he won't be thinking about causes or anything of this. That was a little extension. What I would be thinking in there is perhaps this step that I'm going to show there is interchangeable. It can be done as second and substitution first. But me personally, what I would have done in there, I don't like the e to the minus x. So how I'm going to get rid of it without doing a substitution is as follows. E to the x plus 1 over e to the x plus 2. That's definitely correct. What can I do next? Still no substitution. One more line. Multiply top and bottom of this integrand by e to the x. Look what happens. Times this by e to the x is e to the x. Times this lump by another e to the x, e to the 2x. Times this by e to the x, it becomes a 1. Times this by e to the x is of course 2e to the x dx. Maybe you can see the perfect square in there. If you can't, no problem. Now we have this expression where it's the end of the line, substitution time. U is e to the x. du by dx is of course e to the x. And my dx, rearranging, is going to be du over e to the x. And perhaps, I don't know if I'm going to need it like this. Since e to the x is in fact u, I could write it as du over u. And let's go back to our integral and let's see what happens. This is equal to e to the x is u. E to the 2x is of course e to the x all squared, and therefore that is of course a u squared plus a 1 plus 2u. And what's my dx now? My dx is of course times du. I'm going to use this one because of course there's a reason I can cancel these u's. So this becomes now 1 on the top, du at the end. And what I'm going to do with this one, well, I'm going to rewrite it like a 3-term quadratic in its usual order. And then I spot this factorized. It's a perfect square. Should be able to see it now. So that is 1 over u plus 1 all squared du. And it's of course very simple to integrate. Of course not a log because it's squared. It's a linear adjustment. We can actually write it as u plus 1 to the power of minus 2, because that's of the form ax or au if you want plus b du. And this will integrate by increasing the power by 1 to the power of minus 1. If we differentiate that, a minus will come to the front, no change, and that's going to go to the minus 2. So all we need is a minus to take care of that minus plus c. And of course, the answer, putting back our substitution, should be, we can write at the bottom if you prefer it. I personally do. That's exactly the same as that. All I've done is I put the e to the x plus 1 in there and the bracket the minus 1, so I flipped it at the bottom. The minus, of course, is the minus from there. And I think that's the answer that probably I will be having up there, yeah. Not cautious or anything like that. I just thought I'll show you. And I hope I haven't made any mistakes in what I was just showing you in there, because I'm the king of mistakes. Often I'm a little bit sloppy. Okay, we go one more, and hopefully it's a quick one. I don't mind if it's hard, I just don't want to write a lot of stuff. 138 is tough, but very quick to do. X squared tan of x cubed plus 1 dx. Fairly unpleasant. Okay, why is it unpleasant? The reason is not because it's just hard, it's purely because a lot of people are not aware what the integral of tan x is, which of course you might be asked to prove in an exam, is log of sec or minus log cos, but more importantly is this particular result is given in formula booklets, as far as I know, in every single board. So you need to be aware that this particular integral is there. The second problem with this integral is the structure. Most people, I would imagine, I try to be a student and say, okay, I would have looked at this and my initial thoughts would be quite clearly integration by parts, because I've done a lot of integration by parts and now I know x sine of x, x squared sine of x, something which looks like that is integration by parts. It's a double integration by parts. So this is what the brain sees there, that x squared next to a trigonometric expression. I will be thinking integration by parts. But this is very special because of the argument of the tan. This is the argument of the tan function. If you look at the x cubed plus 1, this differentiates to 3x squared. The x squared is there. The 3 is no problem, we can adjust 3's. So we can do this by a recognition. I'm going to write the recognition and I'm going to do it by substitution because this is not an easy recognition perhaps to do. This starts life as the log of the sec of x cubed plus 1 from this result in here. I'm going to do it by substitution, so do not panic if you cannot quite see where this is coming from and what is going on. Okay, this will go to of course, on differentiation to that quantity, the tan of x cubed plus 1. It will also produce a 3x squared. I just need the third in front of it to make it work. That would be my answer if I was doing this particular integration. Now, for this one, because it's a little bit difficult to see, I'm going to actually do it by substitution. So this is just the answer to compare at the end that we did do it correctly. And of course the substitution for something like this, you can try a few things. And I would have tried perhaps u is equal to x cubed plus 1. That's my substitution. I differentiated du by dx is 3x squared. Make dx the subject. Dx is du over 3x squared. And now I'm going to put my bits in and hopefully this will give me something sensible, something that I can do. The x squared, leave him where he is. I call this u, so that's the tan of u, and my dx is du over 3x squared. Is that good? I think it's quite good because of course the x squareds cancel. So let's see it perhaps better. We got the third, that's the 1 over 3 from the du, tan of u du. And this is formula booklet time or knowledge time. The integral of tan is in fact a standard integral. The third is no problem. You could have written it on the outside better. So you could have written like that. And therefore the answer for this one is a third log sec of u plus c. Standard result up there. And the last thing you need to do is to put your substitution back in. And if you look what I've written up there, a third log sec, and of course the u is the x cubed plus 1, and the integration is done. Okay, we're done for today. 128 to 138. Quite a demanding session. I thought the integrals today were not necessarily long, but quite tough. I hope you followed it. Probably I'll do one more lecture on integration, and then we're through for this particular revision. It's getting a little bit too long, too tedious. I don't know how many people are actually following this lecture now. So I will see you very soon. And who's laughing now?